Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel and it also helps us reach others in need of assistance with the topics on the Civil PE exam. So this will be our first problem in our transportation series, and we are looking at properties of solid bodies. So a little bit of a longer one here. So the description says a spoked flywheel has an outside diameter of 60 inches. The rim thickness is 6 inches and the width is 12 inches. The cylindrical hub has an outside diameter of 12 inches and a thickness of 3 inches and a width of 12 inches. The rim and the hub are connected by 6 equally spaced cylindrical radial spokes, each having a diameter of 4.25 inches. All parts of the flywheel are ductile cast iron with a density of 0.256 pound mass per inches cubed. What is the rotational mass, that's supposed to be mass with two S's, moment of inertia of the entire flywheel? So we have our picture of our description right here with all our dimensions on it. So we are going to have to find the mass moment of inertia, or the rotational mass moment of inertia, for three different parts. The first one's going to have to be with our rim. So our outside portion right here, our rim. Our second one is going to be our internal little circular hub right here. And then we're going to have to find it for each spoke as well, which we will just find it for one spoke and then multiply that by 6 since they are all equal in size. So we are going to do 3 portions here, and then we are going to tally them up in the end. So with our first one, let's work on our rim. So I'm going to call this one X or IX1. And this will be equal to, for our mass, rotational mass, moment of inertia will be equal to pi times rho L over 2 multiplied by R sub O to the power of 4, subtracting off R sub I for our inner and outer radius to the power of 4. So let's go ahead and fill in our values here. And we also have to watch out for units here because everything here is given in feet as our answer, and all our units were given as inches. So we're going to have to do our conversion of 12 inches per foot pretty much everywhere. We have to do our mass moment of inertia. So I'm going to take pi, oh, that's not supposed to be that way, pi over 2. There we go, that looks better. Pi over 2 times our density, which is 0.256 pound mass per inch cubed, times our length, which we are 12 inches here because we are 12 inches thick given by this dimension here. So 12 inches. And then I'm going to do my outer and inner radius here. So I'm going to have my outer, which we are 60 inches. So we are going to be 60 inches over 2 because we need the radius, not the diameter, to the power of 4, subtracting off the inner one, which, well, we are 6 inches thick on each side. So that means we are subtracting off 12 from each side and divided by 2. So we would be 60 inches minus off 12 inches all over 2 to the power of 4, close off our bracket. And then we're going to have our conversion of 12 inches per foot. And this time it has to be squared just because the amount of feet and inches conversions that we need. So calculating all of that out, we get 16,025 pound mass per foot cubed, or per, oh, let me restart. So pound mass, feet squared. There we go. Now I got the right units. All right. So that's our first one, which is pretty good because we're in the relative ballpark of the answer. So it means that, hey, we're looking pretty good because that's the biggest part. So we're going to repeat the same equation, but now we are going to do the hub. And it's going to be basically the same thing because the hub is also a hollow cylinder on the inside. So this one I am going to call X, or IX part 2, which you could also call it for the hub, but basically the same equation. Just interchange our inner and outer radius here. So it's going to be, once again, pi over 2 times 0.256. I'm not going to attach units to this one because it's basically the same thing. 12 for our 12 inches of thickness there, which is this dimension. And then we're going to need that unit conversion once again of 12 inches per foot squared. And then we're going to be multiplying by our outer and inner radii here to the power of 4. So this one will be 12 over 2 to the power of 4, subtracting off 12 minus 6. And that has to do with our dimensions here and what we are told with our inner and outer dimensions of the radius hub, which are all stated up here. And this last one was 12 minus 6 divided by 2 to the power of 4. And this gives us a smaller number of 41 pound mass feet squared. Which makes sense because it is so much smaller than the actual rim, so it should be a lot less um, moment or mass, rotational mass moment of inertia. All right, so now we have, well, we have the rim, we have the hub. Now we got to do a spoke here. So we're going to find a few things about the spoke here before we can actually jump into our mass or rotational mass moment of inertia values. So we have to first determine our length. Well, we know that this total is 60 inches, and we're going to take it off of this X here. So we're going to take 60 inches divided by 2. And then we're going to subtract off our overall width of our hub here divided by 2 because we're going from the center line there. And then we're going to subtract off our 6-inch thickness of our actual hub. And that will give us the length of this spoke in here, which is 18 inches. All right. Now we also have to determine the mass of the spoke, which our mass will be rho times pi r squared for our area times our length here. So rho is still going to be the same. It's still going to be 2.56, and that will be pound mass per inches cubed times pi. We were told about our diameter of our spoke, which is 4.25 inches right here. So we need the radius of that, so we're just going to divide that by 2. So 4.25 inches over 2 squared, and then times the length we just found, which was 18 inches. And this will give us our overall mass for the spoke, which is 65.37 pound mass. All right. So we're going to have to do some little bit of derivation, or not derivation, but difference between finding what our mass moment of inertia what we found for the previous two, because they were hollow circular sections. This is going to be a solid one. So for a solid cylinder, the mass moment of inertia of the spoke about its own centroidal axis will be this, and this is not going to be our answer. This is just going to be a part. So I'm just going to call this one ICX, and this will be M multiplied by 3r squared plus L squared divided by 12. And this would be the equation that you would use for a solid circular object for the mass moment of inertia about its own centroidal axis. So we're just going to plug and chug here. So we would have our mass, which is 65.37 pound mass, multiplied by 3 times our radius of that particular spoke, which is 4.25 inches over 2. And that would be squared, plus the length of it squared, which is 18 inches. And then we're going to divide that by 12. And then we need an additional unit conversion because this 12 is not the unit conversion. So we need 12 inches per foot. And once again, it needs to be squared to cancel out with all the inches squared. And we end up with 13 pound mass feet squared. Now that is not our mass moment or rotational mass moment of inertia here about the center. That is just the moment of inertia or the mass moment, rotational mass moment of inertia about its own centroidal axis, not about the overall axis of the x-axis going through here. So we have to convert this into the same that we did for the previous two for the hub and the outer rim. So we're going to use the parallel axis theorem to find the mass moment of inertia of one single spoke about the axis of the flywheel, that x-axis. So this will be what I'm calling X3, IX3, per spoke. Now this is going to be per spoke. All right. So this will be ICX, what we just found, plus M, which is our mass, times the distance between the centroids here. So D will be, based upon the dimensions that were given, 12 over 2, plus our overall length of 18 inches over 2. And that gives us 15 inches. And that's just giving us our distance from the center of the spoke to the center of X there, or our line, which is the dot right there in the center of the overall wheel. Okay, so let's just go ahead and plug in here. So we have our 13 pound mass feet squared, and we're going to add in our overall mass, which was 65.37 pound mass, times our dimensions, which would be 15 inches. And of course, we need to convert that 12 inches per foot here squared. And that gives me a total of 115 pound mass feet squared. So that's per spoke. So my total for each, or for the total of all the spokes, would just be 6 times this. So 6 times 115, and that gives me 690 pound mass feet squared. So my overall total value for my answer would be the 16,025 added with 41, and then add that together with 690. So my total rotational mass moment of inertia for this entire flywheel would be my first IX1, which would be 16,025, plus my second one, which is 41, and plus the one I just found, which was 690. And that gives me a total of 16,756. And my units would be pound mass feet squared. So looking back up here, which value is closest to 16,700? So remember, I have 16,756. So which one of these is closest to it? Well, it would be C here. And this is the part you got to watch out for in the PE exam, because they will not give you answers that match up exactly with what you found. It will always be the question of which one is the closest type of situation. And you always have to use your judgment call and watch out for your rounding. So our answer would be C for this particular problem, and that's how you would solve it. So I hope this video was helpful, and if you want to see more problems solved this Friday, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel. Also, good luck on the PE exam. Thank you for watching, and I hope you have a fantastic day.